Good. So we will start going live. All right. And we're going live. What is up, everybody? We are live and direct in DoK live stream, not 100. We are now in 101. This is our 101st live stream. And because of that, I made a deal with all of you, our wonderful folks, spectators out there, which, by the way, if you haven't subscribed or liked this video, subscribe to our channel, just do so now and get it over with, because we know you want to do it later, but just do it now. I made a promise. I made a commitment. I publicly stated that if we got 101 attendees for our 101st meetup, that I would live for all y'all, which normally we do afterwards. We put it in a video format, and don't worry, we're still going to do that too. But I feel it's my duty, and it's an honor and a privilege to rap for our wonderful guest today, Alex Gallego, who's joined us from San Francisco. I had the pleasure of meeting a couple weeks ago. So I'm just going to get this out there quickly. It is true also, if we're talking about the data on Kubernetes community historically, we actually started out doing the rap videos first, a cappella. All right. So this is kind of being true to our roots. So let's see how this goes. Please bear with me. This wasn't easy. I wrote the lyrics today. They're kind of fresh. All right. They're kind of fresh. So if, they're, the demo gods are in my favor on my side, this will hopefully go well. Let's kick it off. All right. Alex with no malice, grip the chalice, wonderland like Alice, and gallops at paces with greatness, makeshift, creative but never complacent, face a misplaced monolith, retrace the old forgotten addicts, workload critical mission, reposition your addition, adds up to buckets and blobs, easily scalable, cleaning up those pods, buckets we struck in the cluster, quitando polvo, call me the duster, my folks in Vallejo, near SF, Alex Gallego, keep it close, so Lego my ego. Lego my ego. Ego did not pay me for that reference, for that product placement. But anyway, got that out of the way. More importantly, great to have you with us today, Alex. How you doing?
Oh my God, that is easily the best MC intro of all time. That has to get recorded. If people haven't liked this YouTube right now, I don't know what they're doing. But if they're in anywhere related to data, that is the best intro I've ever had, even from keynotes. Thank you for that. That was amazing. My pleasure. I need to have that. Honestly, as part of my all hands in the company now, I'm just gonna try to invite more. Here's my MC.
You're more than welcome to. We'll cut that out, of the video. We'll get it over to you especially. But more importantly, Alex, like I said, it was wonderful to meet you a couple weeks ago in San Francisco. Now I'm on the other side of the world in Spain. You've got a lot of things going on, but can you just give us a little bit of background about yourself? I'm sure you've explained this a lot, so maybe could you tell us some fun facts that you haven't mentioned in previous interviews or podcasts?
Yeah. So Alex, have been doing streaming for about 13 years, basically my entire professional career. I started playing with Kafka since like 07 in 2011 and Zookeeper 3.2. Anyways, prior to this, I also built and sold the company to Akamai. It was in the stream processing space. So you can think of it as a Spark streaming that I also wrote in C++. A couple of fun facts. One, so the company's name is Redpanda, and is Vectorized, but nobody knows what Vectorized is. Everyone just knows Redpanda. And the way it came about was when I started the company and the product. So I wrote the tech, not even thinking about becoming a large company and kind of having the kind of success we've had. It was really on my laptop, right? So I opened up like Emacs and GCC, and I was just hacking like a future of a storage engine. And so I sent it to like 50 friends or something like that. It's a large number of friends, developers, and I was thinking of like cool nerdy things like vectorized instructions, all sorts of like playing with words around just the things that we do mechanically on the computer. And so I wrote Redpanda somewhere in the middle because in my head I was like, nobody fills out this survey thing, and so we'll see if they actually read it. So it turns out that the Easter egg became the name of the product, and so Redpanda was just like there as like a fun thing for people to see if people actually read and fill out the survey. And like 80% of people, they're like, it's just super cute. It's a really cute animal. And then a second fun fact is the logo of this little cute pet. And for anyone listening into the stream, if you join the Slack, let me know and I can send you some really cute stickers that we haven't even announced. So especially for the DoK, we'll send stickers all over the world. So just ping me and send me your address, and I'll send you one. But the second fun fact is this little pet, this like 8-bit art looking Redpanda. It started out. So at first I hired like a big design firm, and they gave me something I didn't like. Then I went to Colombia and I got a different design firm that I also didn't like. And then my wife reached out to this woman on 99 Designs, and we paid $100 and she was perfect. And so it's just like, so there it is, like spent thousands of dollars, and this woman on 99 Designs built the cutest mascot. And so 2 fun facts that no one has ever heard of before about Redpanda.
That's cool. I mean, well, first of all, with both of those, but I mean, going to the first one, when we say, practice random acts of kindness and celebrate, what is it? Random acts of kindness and senseless acts of beauty. I think that's a really good example of don't be afraid to just take a chance. And there you have it. You get a name for a wonderful thing like Redpanda. And the second one, don't necessarily buy into the biggest brand that you might find. A lot of times there are a lot of hidden gems out there. And we've seen that as well in our community through different artists and musicians that maybe a lot of people haven't heard about, but you get them on here and people realize, wow, this is a great discovery. So I think there's a lot to be learned from that. Now today, we're going to be talking about building a storage engine on top of Kubernetes. Exactly where did this idea come from, and saying like, hey, we're going to do this? How did that happen?
Yeah, great question. So in 2014, when I was building Concord, I thought, right, from a technical perspective, this was before Kubernetes became basically the thing that it is today, which is like this massive, probably one of the most successful open source projects in the history of open source projects. The pace of innovation in Kubernetes is insane. Like it's just it's awesome. So in 2014, I thought, hey, the world needs an oracle, and I was referring to Mesos and Kubernetes as an oracle. But back then, Mesos was really the main sort of stable cluster orchestrator, and so I built a stream processor on top of Mesos as a 2-phase scheduler framework. And what it gave me was kind of, sort of first, we were one of the first frameworks ever, full stop, to be a scheduler on top of Mesos that wasn't in Twitter. I think we were the first enterprise scheduler on Mesos that wasn't at Twitter. And so, so that experience was like, oh, it's really actually super useful to have an oracle that can react programmatically to failure, in particular to failure. But what was most insightful then out of the Concord days was that you have 2 kinds of failures for the systems that I tend to work on. You have stateful systems kinds of failures that are much more complicated, and you need code to react to that kind of failure. And then you have stateless systems kinds of failures. So like, an Nginx. And then for stateless systems, you can actually just write a policy. And so a policy for the stateless systems is like, if the thing crashes, just restart it or scale it or shard it or whatever it is. And the cost of that is perhaps a couple of drop TCP connections, etc. But it's really not, it doesn't have like semantic failures. And now the cost of a stateful systems is really complicated. An example is, if you can't, if the thing that is producing a transaction crashes and part of the protocol uses this oracle, then you can do interesting things like revert transactions or post like a dead letter message that says like, hey, this thing was incorrect to a queue, so that you basically leverage the supervision that Kubernetes gives you to enhance the system. And so, long story short, when I was building this storage engine, I said, there are a lot of sort of intelligence that we can put into the storage engine, and we'll talk about most of those today. And in particular, what is the second half that Redpanda cannot give you that Kubernetes has to give you, right? So the first half is the storage engine. The second half is really, sort of holistic system mechanics. And one of those, an example is, like, everything around the environment is really challenging for the storage system to do itself, and it doesn't make sense for it to do like TLS certificates or DNS, right, or dispatching DNS or supervising that there's a particular number of pods always running in the cluster so that you meet your availability SLAs. And so, anyways, so the idea of partnering with an Oracle really started in 2014 for me in playing around with second phase schedulers. And frankly, Kubernetes one, where like Apache Mesos was recently put into the attic, and it's great, right? Like I think the world needed a unification of the API, and this is really what Kubernetes brings. So that's how I see Kubernetes. Is really kind of as the as a companion Oracle to automate the deployment of infrastructure. And the idea here is that people are drowning in complexity, and these two pieces allows us to write code to have a hands-off system, more or less. Does that make sense?
Yeah. That's a great start, and I really like how you mentioned how where Redpanda drops off. That's exactly where Kubernetes steps in to arrange that. And I think, like you said as well too, the sort of that it's sort of a relief knowing that this battle between Kubernetes and Mesos has since died down, and Mesos now in the attic. Despite being a great technology, that lack of unification I think caused more headaches than help in a lot of cases when talking about automating infrastructure. So anyway, that being said, we're also going to be creating some history here today because Alex doesn't have a presentation. He's going to be drawing live for us. I didn't know that you were much of an artist, but now we're going to be able to see this.
Honestly, if my mom sees this presentation, she's gonna be floored because I am a sticks. I'm like a circles and arrows kind of artist, if you will. And so,
okay.
But we're gonna get through this. Hopefully, it's much more interactive. So I really invite everyone in the audience right now and later in YouTube too, if you want. So ping me offline if you have any questions. But the idea here is I'm gonna walk through presentations, and the design space is so vast that to me, I think if you showed up here, I think you get first pick as what we talk about, and I'm happy to talk about anything from like low-level storage subsystems, which I will do a quick brief 2-slide preso, and then we'll jump into just an interactive presentation. If that
great.
Helps.
Yeah, folks, just remember, feel free to drop any questions in the YouTube chat. If for whatever reason we don't get to your question on time today, you can definitely continue the conversation with Alex in the Redpanda Slack. Already linked that in the YouTube chat. So very, very in the comments, easy to find there. So yeah, if you want to share your screen, Alex, go for it.
Okay, awesome. Let's see. So I didn't really have a presentation for this because I wanted to be interactive. I did want to talk about two things that are fundamental and that actually play an important role in defining a storage engine for Kubernetes. So at the lowest level, Redpanda is, let me start with this. Redpanda uses a thread per core architecture. And this is, I think, fundamentally different from probably most storage engines that I know of. And so the idea here is that there's really two big improvements for storage subsystems from the hardware, right? So the first one is that spinning disk is now, disk a decade ago was pretty slow, right? So you were bounded by the clock tick of the spin, right? So every clock tick of the spinning disk. Most algorithms were around coalescing your blocks so that you would have higher throughput right into disk and ultimately amortize the latencies. So that bottleneck shifted as NVMe devices became 1,000 times faster than spinning disk, right? And so now you can save a page on disk in 24 microseconds. Let's say on like a moderately contended disk, it's around 140 microseconds. And so that's the first bottleneck that is kind of fundamentally different for building modern architecture at the lowest level. And then the second material improvement in computing is that computers are now 20 to 30 times taller, right? So you go from a 2-core or 4-core machine now to 225 core VMs on Google Cloud and 96 VMs on the i3 and Metal instances on AWS. And so how do you sort of construct software for the platform, right? And remember, the platform is always the hardware. It doesn't matter what virtualization platform you're using, the hardware is always the platform. And so the first fundamental distinction here is that Redpanda uses a thread per core architecture. And so it boots up and it says, hey, kernel, like how many threads I have. And this is where Kubernetes, you tell it like, hey, you get access to, with C groups, you say you get access to 3 cores or 4 cores or n cores, right? And so you slice that and then so that's the first. And then it asks the kernel, hey, how much memory do I have? Another C group limitation or security control. and then it takes the memory and then it chunks it evenly across the number of cores that it starts up, and that's all the memory is going to use. And so for those of you that haven't worked with no virtual memory, right? So it's actually really challenging. And so the idea here is
that Alex, one thing really quick, could you zoom in a little bit more?
Yeah, of course.
Yeah.
I'm gonna just present.
Okay.
Is this better?
Perfect. Yeah.
Okay, great. And so so this is similar to Linux kernel style of thinking when writing software, is that, well, the kernel doesn't have virtual memory, and so because we pre-allocate the memory that you give the container, we also don't really work with any virtual memory. And so that's kind of an interesting and different part of architecture, and this will become apparent as to why this matters for Kubernetes. You don't need to have this for Kubernetes. I'm just giving you context as to why some of the later decisions matter. So that was the first one. The second one is everything internally is asynchronous, but this is the slide that matters the most for those in the Kubernetes audience. If you look at this device, right? So this is probably this is an NVMe SSD device. This is a Western Digital. This is actually what was on my laptop at the time I wrote this presentation. And so I benchmarked with FIO, like what is the throughput that this device can actually give, right? So if you're saving data, this is actually how it looks in your laptop. What's the throughput that you can get? And so roughly, I think around 1.2 gigabytes is 1 to 1.2 is really what a sustained throughput this particular device can have. Now, let's look at why a thread per core and an asynchronous model first matters to build a new storage engine from the ground up, right? Like why not extend a different storage engine? Why do you require a re-architecture from effectively bypassing the kernel as much as we could to later being exposed in Kubernetes? The reason here is that let's say that you're on a single core and that core has a 3 gigahertz clock tick. And so you're looking at around 3 billion instructions per second. Let's say that for this particular device, I know because I've benchmarked this device, it's the one that's on my laptop. Just to save a single page is you're looking, 20 microseconds to 140 microseconds is pretty common. If it's uncontended, you can get like, single digit microseconds, like 7, 8, 9 is actually pretty common. And so if you write your application in a sort of sequential fashion where you say like open, read, write, close, you're looking at for just writing the single block, right? So if you say like write, you're looking at around 420 million clock cycles wasted. And so the idea around a thread per core architecture compounded with asynchronicity first, right? So they're co-designs. So the first is taking advantage of vertical hardware, and the other one is taking advantage of how the hardware actually works underneath, right? And so when you combine those two ideas, you get effectively Redpanda, and this is really kind of the pièce de la résistance, or where some of the latency improvements come from for us. So anyways, so those are the main two things that I wanted to talk to you guys about. And so now I am going to stop here, answer any questions, and then I'm going to move to a kind of an interactive drawing. I'm going to join from my tablet. So please feel free to ask me any questions on this slide before we move on to the interactive drawing and talking about Kubernetes.
Definitely. Quick question, Alex. If we're thinking about, I understand at Redpanda, you interact with a fair amount of developers. To make developers, one of the things we talk about with Kubernetes day 1, day 2 operations is how can Kubernetes become more boring so that developers just focus on the things they really need to focus on. When we're thinking about storage and even getting into hardware and the different stakeholders that are going to be involved in this, for the, let's say, average data engineer or even up to architect, what kind of metrics should they be aware of in terms of the stuff that you just mentioned?
Great question. So I think the biggest improvement is actually not the mechanical improvement that Redpanda brings to a storage subsystem. It's actually the developer experience. And so this is actually very counterintuitive. And the reason here is that, we are the storage experts, and the point of raising the level of abstraction for developers, it's kind of like a file system, really, right? So when you're writing a file to your computer, you use a file. Typically, we don't use, well, we use direct IO. You typically would use the file system as an interface, or you don't go and write your own TCP stack, or most people don't write their own TCP stack. And so so that's really what we're trying to do is we kind of focus on this low level bits. But the real improvement, I think, for most people will be the user experience. Now, on the user experience front, the things that people will want to understand for a storage subsystem is really, throughput, latency, CPU utilization, and network utilization. And I actually want to talk about Kubernetes now in the drawing. So, Bart, can you give me access to, from my tablet, it should say like Alex Gallego tablet, so I can join and do interactive drawings and share my screen?
Yes, I can. We also got a wonderful comment from the audience of someone saying, I used to think I was smart until I started listening to Alex Gallego. So one thing real quick, let's get you on here. There we go. I think you should be.
Okay, awesome. Let me join. Okay, so so this is, let me know if
yeah, I see a blank canvas. Yeah.
Okay, perfect. This is great. So let's talk about a few things that we've kind of done in terms of saturation, right? And so you can think of three verticals that you can have basically your network, you can have your CPU utilization, and then you can have your disk, right? And so these are, roughly speaking, the verticals that you get to saturate on a storage device. And so what's interesting is that for network, you really can measure with iPerf 3, and Redpanda should be able to saturate the network at all times. And so what we've kind of done is we really optimize for this right now, right? And the reason is, if you're sending a gigabyte per second, then that's just like your business requirements, right? And we can optimize the network actually with compression. I'm just kind of answering your first question, Bart. So you can optimize the network with a little bit of compression, and you train in a little bit of CPU. And when we talk about WebAssembly and the trade-off of CPU for network and disk utilization is, but these are the levers that you can start to think about. And so the reason here is that if you look at the clock tick of a spinning disk, let's say, right? So because the latency moves to, let's say, 24 microseconds, just as picking a random number. So then what happens is that if you're blocked on a thread of execution, what using an asynchronous framework allows you to do is allows you to optimize the CPU, because what happens is you dispatch the IO, but then you go and you do other useful work. And then later in the future, you come and you reap the events, as opposed to having this kind of sequential, right? So the difference is you move. So let's say from, I don't know, I'm going to give this a number, to like 10 units of execution, or let's say 10 milliseconds, it doesn't matter what it is, to let's say like 8, right? And so I'm making up numbers here. And so that's what using an asynchronous framework allows you to do. So you submit the events to the hardware, and then later on you can reap those events. But in between, if you're using a cooperative multitasking framework, it allows you to suspend that thread and say like, hey, I'll reap these events later. And so ultimately what this means, and I'm going to create a new slide here, is that you're really leveraging the hardware as much as you can. Now, so those are the metrics that you want to use. I do want to talk about Kubernetes actually as some of the fundamental things that we do. So we added an anti-entropy mechanism to embed it in Redpanda proper. We actually didn't make this an enterprise feature. So every single user of Redpanda gets to leverage this anti-entropy mechanism. And this is when Kelsey tweeted about Redpanda, this is like one big fundamental feature that if you are working in a dynamic environment like Kubernetes, like you have to have this. And what the anti-entropy does is that it fixes workload skew, right? And so the idea here is that let's say you have.
Sorry, Alex, got a quick question from the audience, from Evan. What's up, Evan? Evan's question, and Evan is no stranger to the world of storage. Any thoughts on impact if any of NVMe -OF would be cool as well? Does it lead to disaggregated as opposed to the use of local storage? Saturating the network suggests keep the data local.
Yeah. Can I point on that? So okay, let me answer that question quickly, and then I do want to finish the thought of anti-entropy. You could use both, and I think it's all about cost for some people, right? Like as long as the block device is exposed, there are some benefits to having local devices, especially in conjunction with the WebAssembly engine that we've talked about. And the idea is like, how do you materialize locally without hopping the network? Because if you hop the network, then you end up ping-ponging your data, and so it does work. But for people that have worked at the storage level, well, typically, if you disaggregate computer and storage, you have a separate NIC, right? So you have two NICs in your computer. One NIC is like the workload NIC, and then the second NIC is the substrate of the disaggregated storage, so that you can give determinism and SLAs to the workload network card. And so it requires much more sophistication. This is exactly how EBS works on Amazon, right? So like Amazon, they have a separate network and a separate NIC effectively. I don't know actually physically how it works, but I do know that they have a separate network on EBS volume. Same things with GCP. And so so you can have this aggregation of a storage. Typically, disaggregated storage will have a 3x internal replication. And so when you compare it with a Redpanda workload that already has a raft and transactional mechanics, you end up replicating your data another 3 times. So anyways, hopefully that answers your question. So it's a trade-off that you just have to be aware of, that the cost may vary from, may explode from 3x to 9x. If you end up using disaggregation of a storage. But if you are running your own disaggregation, the one thing I recommend is to divorce your workload network from your storage substrate network so that you can give determinism to the SLAs. Okay. Actually, bounded SLAs. Does that make sense?
Yeah. And we had one other question, separate question. Are you using IO Uring?
Great question. So not yet. And the reason is IO Uring is only about 5% faster than libaio if you were using the asynchronous RIP interfaces. So we use Sistar as the underlying framework, and Glober, who is a friend of mine, actually invested in his new company. He did this whole profiling and benchmark, and there's a public thread on it on Google mailing list. And so at the end of the day, when you measure like end-to-end workload impact, it's significant. It's like 5% or so, but it wasn't like 3x or something like that. And the reason is the asynchronous framework that Sistar was using. So it basically you submit 128 IOCVs, and then you can rip them asynchronously as well, and that require a kernel patch on 4.19 and above. So the executive summary is not yet because it didn't have that significant impact. We're still going to do that, and so we hope that we have a chance to work on this kind of not so low hanging fruit, but right now, Redpanda is already so fast in comparison with its peers that we haven't had the need to squeeze this 5% performance. We will at some point. Okay.
And then we got one more follow-up question, but I'll let you keep going. We can get to it. We can get to it afterwards.
Okay, awesome. So let's talk about anti-entropy, as in the function of Kubernetes. So here's an interesting workload. And so Redpanda uses a stable leadership work protocol. And so for those in the audience, I have to cover everything from distributed systems to kernel bypass to Kubernetes, because they're all co-designed. They're not sort of like separate designs that you think of. And so the Kafka, the protocol, right, it uses a stable leadership semantics. And what it means is that when you have a client connecting to, let's say, a particular leader, it expects the TCP connection to be stable, right? And so the alternative here is that you don't need a stable protocol to save data onto a cluster, right? The alternative is that you do what the classic single Paxos gives you, which means you do a voting round for every time you save a piece of data onto the cluster. You go from an acceptor into basically a committer, and then and then you commit the data and then you respond. But that introduces an extra round of tardiness. And so what you're looking for in the Kafka protocol to keep semantics equivalent to upstream is you're looking for stable leadership. So that sort of declassifies a large literature background on non-stable leadership protocols for the consensus round. That's important on the workload SKU in just a second. So a client application, your app, connects to the leader in a Redpanda broker, and so it connects to the leader, and then the leader, we use Raft, and this is fundamentally different. So this is a quorum system, and this is fundamentally different to like ISR, which is what upstream uses. And so you can think of ISR as like a chain of the weakest. And we wrote a very detailed blog post on this. Is the latency that you get on an ISR acknowledgement chain is the latency of the worst behaving node. The difference between that and a quorum system is that the latency that you get from a quorum system is the best of the majority, right? So you go from worst of the link to best of majority. That's a pretty detailed distinction and something to keep in mind. So let's say this is worst. Let me just write it here. Worst of chain, and then this is best of majority. Majority. And so, okay, so anyways, let's talk about work anti-entropy. So when you connect it into this node, and then let's say that these are followers, and everything is great. And so now let's say that you have another customer, right? Another client connecting to a leader. And now all of a sudden, it turns out that this node is responsible for 80% of the traffic. The issue with this is that then, your saturation is going to be, this link, right? Like that particular node can only handle so much network connectivity. The CPU is going to be spiked, right? Meanwhile, the other followers use an internal RPC framework that it has been, optimized for leader endian encoding, pretty similar to the flood buffers that I wrote. I actually contributed a couple of patches to flood buffers before I decided to write my own internally for this storage system. And so anyways, so let's talk about the skip on the anti-entropy mechanism. The idea here is that if you have 80%, you're not using your cross-sectional bandwidth. And so the cross-sectional bandwidth is the idea of like what happens in the totality of the cluster, like what is the actual bandwidth available in the cluster. And so now going back to this, and so what the anti-entropy mechanism says is that right now is, it's active and it only has one mode. We hope to expand this as the number of partition leaders. And so now when it detects, there's a loop in every node, actually in the controller. And so, imagine that you have an oracle. You have an oracle, and the oracle is like inside the Redpanda cluster. Basically, the code design is the oracle of Redpanda coexisting with the oracle of Kubernetes. And so the oracle every 10 milliseconds or so, and it understands, because of Raft, like who has leadership of what. And so it says like, hey, this has 80%, and because you have 3 nodes, this should really come down to be, basically 33% leadership, and it'll start a migration of leaderships to the other nodes, so that when a new client comes up, it'll connect to, so every node is a leader and follower of some other particular groups. And so when new clients connect, they're going to come into the other nodes. And so you start to leverage this particular cross-sectional bandwidth of your cluster. What it means for the user, if we go back to the particular, to the first kind of levers that you have in a storage subsystem, is this really starts to optimize the network piece, right? And also the CPU, but not the disk, right? So that the anti-entropy mechanism is an optimization to optimize both disk and CPU. And the reason here is like, how do you move the bottleneck from away from one node into multiple nodes and leverage the cross-sectional bandwidth? Any questions here?
We got a comment that this all sounds like very much first principles design to me, which is great.
Okay, awesome. So let's keep moving on as to some of the things that we've done. And so let me try to prioritize the time here because we don't have that much time left. So remember that Redpanda I talked about as being a quorum system, and the importance of being a quorum system is if you have a log. So what a log gives you as an abstraction is immutability. This is not true with other Kafka API implementations, for the record, right? And so we use a quorum system. In particular, we use, actually, let's talk about specifics. We use Raft. And so where Raft gives you 3 semantics that are important for Kubernetes. So first of all, it says you cannot have a gap in the log, full stop. You can have unavailability of a particular partition, but you cannot have a gap in the log. And so this is not true with actually the majority of the other streaming systems. Because they use different replication protocols and different recovery mechanics. The idea here when you benchmark is, to me, when I was designing this, hardware is so good now, we can actually use good protocols. And, like networks are sustainable when you can rent 100 gigabit per second NICs on Amazon and so on. But this is exactly what a developer wants. And so when a developer sends a message, and then they consume the message back from the queue, they literally expect this kind of behavioral semantics, even if they don't articulate the mechanics that they're sort of expecting it, right? The idea here is on a pub/sub system, and ask anyone what pub/sub is that isn't an expert. You say, like, what is pub/sub? They'll tell you this words almost word by word. They say, hey, I publish a message and then I can consume the message. They never go back and tell you, well, depending on if you configure your brokers to flash your messages and to act and only act once it's being replicated to a quorum, and the quorum has saved it to this so that you can survive multi-availability zone failure and you can survive different correlator zone failures. That nobody says that because that is too complex for the developer. And so that's why I actually, when designing the system, I studied with chain replication. And I was actually talking with Mahesh, who's now at Facebook, who wrote the Corfu paper a couple of days ago. Really, the downside of a chain replication system is that you always need metadata. And then once you build the metadata and recover, you end up with something that looks a lot like Raft. And so Raft gave me and then transitively the developer the mental framework to understand basically safe semantics of what it means to publish and subscribe fundamentally. And so this is important in the context of Kubernetes because it means if you transfer leadership, right? So from one of the leaders to a follower, let's say that this node crashes, you still have high availability, right? Like it gives you a mathematical proof. But most importantly, and this is very subtle, is that it tells you once you elect a new leader, so let's say let's mark one of these nodes as the new leader, then that leader has an up-to-date replica and there are no gaps in the log. And that's actually how people tend to reason about this system. And so now in a dynamic work like Kubernetes, I also speak really fast, so people in the audience, please feel free to stop me and ask any questions. In a dynamic system like Kubernetes, like you're probably going to lose a node all the time. Like it's Kubernetes. In fact, people like nuke clusters all the time because it's very easy to nuke a cluster. Like the configurations, Kubernetes is so developer friendly that I've seen people actually nuke production clusters in general, not related to Redpanda, but to services. I actually think it's this upside is that it's so easy to use that people feel comfortable running in their laptop. So, anyways, so to stay on track here, once you transfer the leadership, that is the semantic that it gives you. And again, this has to be co-designed, right? Like in the era of Kubernetes, in that pods are dynamic and they'll come in and go, and you need to like upgrade the kernel of a particular node, blah blah blah. So this is another like important distinction of the storage engine. I want to talk about two more important things. One is kernel optimizations, and the other one is tiered storage as kind of like big areas of expertise. Excuse me, big areas of improvements to be able to run a storage subsystem on Kubernetes. Let me know if you have any questions.
No, you're good. You're on a roll. Keep going. Keep going.
All right. So let's talk about kernel optimizations. So you don't have to do this to run Redpanda, but if you care about latency and throughput, we have a command called rpk tune. This is also in basically the GitHub, so you could run it yourself. This is not an enterprise feature. So everything I'm talking about is actually just out there for everyone to use, except tiered storage, which we're releasing probably in pretty soon. So stay tuned. So RPK tune, what it does is that it probes the hardware. And so a couple of things that are important. So it turns out that if you have a multi-core subsystem and you have a NIC, every core has basically 2 queues, basically send and receive. I can't even spell, but you get the gist. And so what multi-queue says is that every NIC can basically interrupt and rip and consume from the same core. And so that's one optimization. Another optimization is that on the block scheduler level, right? So let's draw 2 subsystems, right? So first, this is the block device layer, and then here sits the file system, and then here sits the kernel, and then here sits like Redpanda and Redpanda. So assume that you have this, right? And like this is it. This is the actual device. This is the NVMe device. Actually, technically here, because there's the NVMe controller, CTRL, and then actual calcogenites. Like the actual metal is here. So let's talk about these two use cases that are important for latency. So the first thing that we do is we really tell the kernel 2 things. We, the storage engine, actually completely understand the layout of the block device. Frankly, the Linux kernel tells you that, right? Like you can say like, hey, file system, what is your page line alignment? Blah, blah, blah. And then the file system will say like, oh, like I have been configured to give you 512 byte page alignments or a megabyte or 4096 alignments. And that's basically it. So what we do is we tell the Linux scheduler, don't coalesce the IOs. And the reason is Redpanda works on hardware aligned memory. And again, remember that we boot up, and you don't ever have to do this, but it's important to run RPK tune if you actually do care about latency. And so what the kernel is trying to do is trying to give the general developer effectively sound primitives to reason about. And so when you open a file, that file typically comes with a page cache, which is like another object, right? You can think of it as a map mentally. If you're writing code, this is like map, let's say string to string, right? And it's not that, it's more sophisticated, but assume that, and then it's like an offset to data, right? So it's actually an integer to a much more sophisticated data structure, but let's say an integer to a string or an integer to like a byte array. And so anyway, so we align this thing. And so there is no point, and in fact, we don't want the block scheduler to coalesce the IOs. And so if you have a file and you're streaming writes to a file, you can say like hello world and hello Bart and hello data on Kubernetes, blah, blah, blah. What the Linux scheduler will do is like, okay, cool, I'm not gonna do anything. At some tick in the future, they're like, oh, look, there's a bunch of little IOs. I'm going to create a new block. And then I'm going to copy these things, align them, and compact them into a single page. And then I'm going to save this, as opposed to dispatching multiple pages, right? Because what ends up happening is that you end up consuming the bandwidth of the device for actual data. And so this has huge material improvements for standard IO workloads. And so what we did is we tell the kernel, don't coalesce the IOs. We're using hardware aligned memory boundaries. We want to track it ourselves. And so we don't use, this is kind of, when we don't use the page cache in addition to, and I'll talk about that in just a second. And then we also, tell the kernel to not coalesce the IO, and then to use a FIFO dispatch queue for the actual underlying storage, right? So like the communication between the block device and the NVMe controller will happen on a FIFO basis. And we choose on the application, actually the IO CBs and hardware alignment that we want the kernel to save to source. What am I trying to say here, and how does this relate to Kubernetes? So the second thing here, to answer that question is, you don't have to do anything with Kubernetes, but if you do care about latency, then on a pod, when you start the pod, I have to come back to this thing. Basically, as an init container, you run RPK tune, and then typically you would run Redpanda it depends on your workloads. We typically recommend if you actually care about squeezing latency, then we recommend like you can take the whole machine. But again, here's what's cool about Redpanda is all of this is optional. Like the system is intelligent enough to figure whatever the environment gives you, and it'll just work, right? So you can run it on your Mac laptop on like the Docker VM on your Mac, or you can run it on a 96 core VM on an IE3 EN metal with these tuners, or frankly, you can run it on ARM. We support ARM, and it doesn't matter. Redpanda will figure out, well, what are the things that the developer or the deployment operator gave me, and it'll try to do its best, right? And so the more optimizations that you push onto Redpanda from like the hardware level, the better it'll run, but you don't have to. So I think that's another key principle. You never have to go all the way in. Like you can spin up. In fact, we have IoT users that for a comparative workload, they actually run the entire workload on a single core because Redpanda is so efficient at doing its job. They had clusters with like Zookeeper and other competitors, and they're like, hey, I just need a single core, and maybe I'll use 3 cores, and it's fine. For their workloads, they really they care about sub-second latencies. They don't care about microsecond or like low digits milliseconds, and so they don't care. For them, they're throughput bound, and it's mostly a mental model. And so we're giving just you tooling to reason about. Anyways, to stay on course with Kubernetes, because this is all about Kubernetes and not search engine, is you can say RPK tune all, and it's one command, right? There's nothing you have to do. It's one command, and then RPK has intelligence, and it'll do a few things. It'll detect if you are on GCP, and it'll disable a couple of firmware optimizations that made GCP storage absolutely atrocious for tail latencies. Like it's terrible. It's actually great for the average application developers, and it's terrible for people that understand storage. I think Amazon has a better storage story there. So anyways, RPK tune does, and it's everything from like figuring out which cloud you're running in, to the actual device that you're running in, to like what tuners are available, what like /proc tuners that you have, and it'll just do it all, right? And so you don't have to worry about it. There's documentations, and you can turn them on and off separately. Anyways, and then you run Redpanda, and then you tell Redpanda like whatever C groups limits you give them, and then it'll kind of just work. Now, the second thing, I do want to go back here to this, and then I probably just have to wrap up for questions, and I'll mention tier storage. We don't use the page cache. So when you start a file, the kernel gives you an object like a map, and so what it introduces for a storage system is introduces latency and jitter and unpredictability. The reason is when you read a page, this page cache thing will like, oh, you're gonna read a page. I'm smart, and I'm gonna fetch the next 10 pages. But I was like, no, you don't understand. I'm a storage engine, and I can tell you exactly what I want with protocol semantic information that the file system could never have. And so when we're trying to squeeze performance out of the hardware, we have to understand that the file system, for us, a storage system, transactional storage system, it introduces latency and unpredictability. And the reason is, if the file system starts doing this for every file handle, and let's say you have 100,000 file partitions on a particular machine, or 1 million, then you end up saturating the throughput of the device for wasted work instead of actually doing useful work. So in the low tiers, right, when you aren't trying to saturate the device, it's probably fine, really. So what if it introduces a millisecond of latency? Most people, are not at that level anyways. But the problem is at the limit. Like, what happens when you start to saturate the device? Well, then at the limit, your device is stuck doing a bunch of wasted work and is wearing and tearing your devices and actually not doing anything meaningful for the application. And so it's kind of like why computers feel slow today. One more thing on the storage engine, and then I honestly have to wrap up for questions because we're at the top of the hour. But we've talked about, I think, the most semantic thing. So the last one is transparent tiered storage. So this is probably the coolest thing that we've done, and stay tuned for a very in-depth blog post of how we actually make this happen. And so the idea here is that if you have any S3 compatible APIs, so Minio, GCP, AWS, Azure Blob Store, they all provide the thing because S3 API is dope, or Cloudflare even. So let's say that you have a leader and then you have a couple of followers and you're trying to save some data, right? And so what happens is, let's say in total, this guys, actually let's do arrows. These guys have, let's say, 1 terabyte of disk locally, right? And it's replicated, which means that is really like how much disk does one node have, if let's say for this particular deployment. And so what happens is, so you have 1 terabyte, but most people, what they do for disaster recovery is for all data, right? For let's say the previous 10 terabytes or petabytes, it doesn't matter. We have a user that's pushing 12 petabytes of data to cold storage. Is this 10 terabytes will simply be uploaded automatically for the user. But here's the important thing. If you have a client application that is consuming, let's say you have a client and this is a particular leader for that partition, it'll go and it'll fetch lazily some data into a local scratch space, TCH, and render the read transparently to the Kafka application. This is, I think, the third, probably most significant change for a storage system to work with Kubernetes. It's like you have to plan for a total system disaster. And so the total basically data loss window right now for most deployments, given this modality, is around 10 minutes. Right, and this is assuming a correlated failure of your entire cluster, right? And so you can mitigate that if you have multiple availability zones, right? So let's say that if you have multiple AZs, and so really is what is the probability of basically all 3 zones failing at the same time for you to have this particular 10-minute failure. And so what happens is every 10 minutes, we seal a segment. So as you're writing data, let's say here, right? So this is one segment. Say you're filling this data and it's going great. Every 10 minutes, and you can configure this, you can seal it. And once it gets sealed, it gets uploaded onto S3 as an OS segment. And we're actually adding more intelligence on it, but this is roughly a better mental framework. It'll seal it, it'll upload it so that if you have total system collapse, you can actually start a Redpanda cluster in 150 milliseconds and have it render reads right now. It's kind of magical. And this is the only feature that I've talked about that is enterprise. Anyways, I think I should break for questions because we only have 8 minutes left and I've been talking like a maniac for the last 40 minutes.
You've been getting a lot of stuff in there, and the drawings certainly help. And I think this is something that we're going to be telling all of our future speakers if they can draw, because it brings it to life in a different way and you get to see all the different connections. So one question, here we go. I think that most cases using Kubernetes, you cannot get really persistent local disk, and because all real persistent disk is remote. I guess you need some kind of co-op between fast NVMe or remote.
So remember that this is all optional. You can, we have some users that use network devices, and frankly, I think we also recommend that. It's really all about what you're trying to optimize for. Let me tell you when it doesn't make sense. Let's say you have an IoT stored and forward use case, or we have this oil and gas pipeline use case. They basically do a bunch of bulk imports, they do a bunch of processing, they kind of throw it away. They don't really want to pay the cost of network disk. And so it is true that disk is a pain in the ass, it's very challenging to work with, especially with cloud Kubernetes vendors, and it is network. And so think of this more as like tools and just, use what makes sense for your use case. If you want to chat with me or my team, feel free to ping me on Slack. And we do a lot of consultative kind of architecture discussions for people, and then we just help. We don't really, we just tell you like, this is actually how the hardware is working. This is the optimizations that you can make. Does it make sense for your use case? But it's true that this is the pièce de la resistance, is how you deal with disk. And so this tiered storage and the local disk optimizations, they're just there available for the use cases that make sense. We do run some of our cloud in local disk. So it is possible. You just require a lot more tooling. Like a lot more tooling, like a team of 15 people basically tooling. And we can afford that because we're in the service, we're in the business of giving a storage system to people.
Very, very good. Positive feedback to that answer. Now, once again, going back to the stakeholder question, it seems that the tool belt of a developer is maybe getting bigger, that there are other things that have been taken into consideration regarding storage that perhaps weren't there if they're going to be working in a Kubernetes environment. Would you agree that developers can't go without, they cannot ignore this, that this is something they need to be taken into consideration? And to make that easier, obviously, we have the data on Kubernetes community, there are other spaces. But what do you think about that? Looking back to, 10 years ago in terms of how things were, perhaps maybe a bit more siloed. What's your take on that?
Yeah, great question. So I was just drawing this slide, and it's like assume a uniform distribution. I think that streaming and storage subsystem has largely been for experts, experts by experts. And really what Redpanda and other storage subsystem, I think Cockroach is another good example. It's like, sort of pushing on the complexity curve away from by experts for experts, but you have to get this crazy idea of certifications to be able to run this. I mean, I know things like you may want that for really people pushing the envelope, but my take on it is really a different design philosophy. It's why not make it super easy? Why would the storage experts push the complexity of this thing onto the users? And that's really kind of the trade-off that I see here, largely made by other projects is, and so to talk about in particular in Kubernetes, I think this is really a fundamental framework that people write in storage engines and frameworks and author have to do. And this is why Kubernetes won, in my view. It was actually the developer experience was beautiful. It's you can get it started in comparison with other things. And really for large companies, if you are getting started on a Linux, PHP app on Apache, then there's better developer experience. But when you're trying to kind of productionize workload with security, etc., Kubernetes is actually a really fantastic API. So anyways, I'll stop there. And I think this is the real innovation that is happening with a lot of frameworks like PlanetScale and Cockroach and Redpanda, and we're really focused on how do we make this for non-experts? And so it's really expanding your toolkit and making it accessible for a larger audience of developers.
I think that's great, because to feel that it's not siloed, to feel like there's not necessarily that kind of gatekeeping that can go on with those things sometimes too, and really empowering people that previously may have been somewhat marginalized and left out of the equation. We've got a little bit of time left, so I do want to ask you a question that we've been asking speakers lately. If you had to choose one person, historical figure, it can even be superhero, to run data on Kubernetes with together, who would it be? Who would be your first pick for your team? It can be singers, it can be actors, it can be like I said, it can be fictional characters, it doesn't matter.
So is the question who would be like a sidekick that I would
Exactly.
Oh man, I think that's a really great question. I'll probably just bring a DJ. Man, it's I listen to a lot of minimalism in general, so it's just random minimalism that I hear on the internet. I'm trying to think. It's either that or maybe someone like Minor Threat, who's a punk rock artist from 1984 era in hardcore American punk rock. Just because sometimes things don't make any sense and you feel so angry, you feel like smashing your keyboard. And I felt that listening to Minor Threat would just give you a way to, it's jump around and scream without actually breaking things. So that's a great question. I don't know. I need to think on the minimalism side when things are actually working. I feel like there's a duality of personalities there.
I like both. I like both because I can see that you can embrace both. Embrace the chaos with Minor Threat. When you get into that kind of groove, the minimalist side would be more helpful. Now we don't unfortunately we don't have a lot of time left, but just to recap, there's a lot of stuff to unpack there, right? And we'll be doing that in the next couple of weeks for sure. Once you get the transcript up to get this shared with everybody. Had great feedback from the audience, great attendance. We do have one question though, just really quickly, from Mohammed. Have you considered a declarative interface to hide complexity? If you can answer that really quickly.
Yes, I think that's on us. That's on like the roadmap. I think there's complexity on management, and then there's complexity on interactivity. I think Bentos is pushing the envelope there in terms of process and interactivity as a declarative function. I think it's on us still to expand what developers need to do to just bootstrap the infrastructure. So hiding complexity is not a one-stop thing. There's like hiding complexity at every level is important.
Very good. Cool. Nice, succinct answer. Before we finish up, as always, while you were drawing, we had somebody else drawing in the background. So I'm going to share my screen real quick. Let me know when you can see it.
I can see it.
Good.
Oh my God, this is amazing.
So yeah, so our amazing graphic recorder, Angel, is always in the background, listening to what's being said by the speaker and creating a graphic representation of that. There was a lot of stuff that was covered, so I think you did a very good job in the limited time that was available to get that done. Alex, it was great to have you. We've done, like I said, this was live stream number 101, and the energy level was really good. We got some great questions from the audience. If you want to continue the conversation with Alex, please check out the links that I shared about Redpanda. Get into that GitHub repo that I also shared as well too, so you can take a look at the documentation, get underneath the hood a little bit more, dig into the weeds. But also feel free to reach out to the Redpanda Slack. Lots of things going on there. Some great users, some great use cases. Alex also is really easy to find on Twitter. Just Alex Gallego, I believe. Yes.
No, oh, it's Emacs no, the largest error in the Linux kernel you can find.
Ah, very good. Okay,
kernel,
okay. Yeah. So it's no coincidence that we talked a lot about kernels today. That's good. Anyway, Alex, thank you very much for your time today. Really appreciate it. Folks, we'll be back next week with more live streams on Tuesday and Thursday as usual, and looking forward to deliver more great DoK content. We've also got Twitter Spaces tomorrow. If anybody wants to hang out, we'll be talking about the history of data. I'm looking forward to that conversation. Once again, Alex, thank you so much for your time today.
Thanks for having me, Bart. Bye, guys.
All right, take care. Cheers.